again in our laboratory. From the previous video, we talked about potentiometry, potentiometric titrations, and potentiometric pH measurements. But for this video, we will be talking about redox titration. But before that, let me introduce our learning objectives and our conceptual framework. And now, let's start the discussion.
Good day everyone, my name is Michael Martinez and today we will going to tackle about redox titration. But before that, let's go back to the history of redox titration. Who discovered the redox titration and how it started? A modern exploration of the oxidation-reduction reaction started formally with Georg Ernst Stahl in 1697, when he proposed the phlogiston theory, which was based on the premise that the metals often produce a calx when heated. Moreover, the calces form metals when heated with charcoal and wood, and charcoal is particularly rich in phlogiston because they leave very little ash when they are burned. However, the theory of phlogiston was not widely accepted in the scientific media. So Antoinette Laureate Lavoisier came with solid explanation of combustion. In 1772, Lavoisier discovered that when elements combine with something in the air, it can produce acids. In 1779, Lavoisier coined the name oxygen for the element released by the decomposition of mercury oxide, and from here, explanation of certain reaction as oxidation reduction finally started. Now, what is redox titration? Redox titration is a laboratory method of determining the concentration of a given analyte by causing a redox reaction between the titrant and analyte. This type of titration sometimes required the use of potentiometer or a redox indicator. Redox titration is based on an oxidation-reduction reaction between the titrant and analyte. It is one of the most common laboratory methods used to identify the concentration of a known analyte. In order to evaluate redox titration, the shape of corresponding titration curve must be obtained. In this type of titration, it proves convenient to monitor the reaction of potential instead of monitoring the concentration of reacting species. As discussed earlier, redox titration or redox reaction involve both oxidation and reduction. The substance that donates electrons in a redox reaction is what we call reducing agent, while the substance that takes electrons in a redox reaction is what we call oxidizing agent. In reduction, a substance can undergo reduction can occur via the addition of hydrogen, the removal of oxygen, the acceptance of electron, and a reduction in the overall oxidation state. In oxidation, a substance that undergo oxidation occur via the addition of oxygen, removal of hydrogen which was attached to the species, the donation, loss of electrons, and an increase in the oxidation state exhibited by the substance. Thus, it can be understood that redox titration involves a transfer of electron between the given analyte and the titrant. An example of a redox titration is the treatment of an iodine solution, which is reducing agent. The endpoint of this titration is detected with the help of starch indicator. The principle of redox titration involved in the oxidation and reduction titration is that the oxidation process involves the loss of electrons, whereas the reduction process involves the gain of electrons.
So let's proceed to our next topic, which is the redox titration calculation. So we will be calculating the concentration of the iron sulfate solution. In order to solve the given problem, we need to follow some steps. The first step is write the balance equation or balance reduction of half of the equation. So we have MnO4 negative plus 8H positive plus 5E negative. The product is Mn2 positive plus 4H2 0. So our next step is we need to write the balanced oxidation half equation. So we have Fe2 positive, Fe3 positive plus E negative. Number 3 step is we have to write the balanced redox equation. So our reduction equation is MnO4 negative plus 8H positive plus 5E negative, which is cancel. And our oxidation equation is we have 5Fe2 positive, and the redox equation is MnO4 negative plus 8H positive plus 5Fe2 positive. The fourth step is we need to extract all the relevant information. So we have MnO4 negative is equal to 0.0484 mole L negative 1. And then the value of our volts is 15.50 ml. The fifth step is we need to check the data for consistency or convert volumes in ml to L. So we have MnO4 negative is equal to 0.484 mole L negative 1, and the value of our volts is 15.50 times 10 to the power of 3 liter. The sixth step is calculate moles of known reactant or our titrants. So we have the value of our N is C times the volts is equal to 0.484 times 15.50 times 10 to the negative 10 cube is equal to 7.502 times 10 to the power of negative 4 mole. The seventh step is we need to find the mole ratio from balanced redox equation. So the value of our MnO4 negative is 1 and our Fe2 positive is 5. The eighth step is calculate moles or the N of Fe2 positive. So the value of our Fe2 positive is equal to 5 times 7.50 times 10 to the power of negative 4 is equal to 0.003751 mole. And the last but not the least is we need to calculate the concentration of Fe2 positive. So is N divided by the volts is equal to 0.003751 divided by the 25 times 10 to the power of 10 cube is equal to 0.1500 mole or L1.
Now, let's proceed to redox titration methods and procedures. Redox titration methods is easy to use if the quantitative relationship between two reacting substances are known. These are the things that should be remembered when doing titration. First is always rinse burette with water, not from the faucet but from the beaker. Second is fill the burette with the titrant using a funnel. Third is fill the burette tip by momentarily opening the stopcock. Fourth is now that you are ready to read the initial volume, remember that burettes are graduated in a downward direction. The first estimated digit will probably be the hundreds place. Fifth, do not waste time in trying to fill the burette to 0 for each titration. Sixth, do not start above the 0 ml mark or titrate past the 50 ml mark. Seventh, always use white paper underneath your sample flask so that you will notice a slight color changes. 8. Learn to swirl the flask without removing it from underneath the burette. 9. Use a drop, drop, drop paste until you see the color change becoming more than local. It is where the titrant meets the sample. 10th, The second and the third trial titration should always be fast, assuming that the sample will be about the same because you know approximately how much titrant is needed. If the first titration required 25 ml, then you can add 22 ml all at once and then proceed cautiously. Number 11. Remember that the amount of water used to dilute the sample is not crucial because it does not affect onto how many of the sample molecules are present to the same flask. Diluting with water allows you to see the color change easier. Number 12. Always rinse the sample flask before using it. Number 13. Always label multiple burettes and flask. Number 14. Always ask yourself upon doing the titration, did you add the indicator?